Inverse relations. Okay. Every operation in mathematics has an opposite or an inverse. It's what allows us to solve equations. So we say, how do we get the pronumeral by itself? We undo the operation, or we do the inverse. So you have x squared, you do the inverse of squaring, which is square rooting, and so on. Well, functions are the same. So if you've got, well, let's say the log of x, and you want to get x by itself, you perform its inverse, which is an exponential. So they would be inverse functions. So we're going to talk a bit about this. Theoretically, we won't be tested on this till next year. But seeing we're talking about functions, and there is an exercise on it in the book, I think they label it extension in there. May as well look at it now while we're talking about functions. So first of all, an inverse relation. So if y equals f of x is a relation, then its inverse relation is simply obtained by swapping the x and the y around. Okay? So y equals x squared, its inverse relation would be x equals y squared, and so on. So x cubed plus x, inverse relation, x equals y cubed plus y. Now, what then happens, because we swap the x and the y's around, the domain and the range will interchange as well. So the domain of the original relation will become the range of the inverse relation. So if the original one had a domain x is in between 2 and 3, then the inverse relation would have a range y is in between 2 and 3. And the same thing happens with the range. The range of the original one becomes the domain of the inverse. Okay. And if you were to draw both of them on the number plane, you would see some symmetry. They would reflect in the line y equals x. So visually you can tell whether a function is its own inverse. If it's symmetric in the line y equals x, it'll be its own inverse. And there is a shape up there that would satisfy that. Which one? Well, the hyperbola is the one I'm looking at, yeah. If you imagine y equals x as a mirror, or a line down there, it would be reflected either side. The circle, true, because obviously it's symmetric everywhere. It doesn't matter where you put it there. It would be its own inverse relation. Y equals x squared, domain's all real x, range is y is greater than or equal to 0. So its inverse relation, x equals y squared, domain x is greater than or equal to 0, range will be all real y. So they swap around. Okay, so what's an inverse function? A couple of rules it has to satisfy. The original thing we're going from has to be a function. Okay? So the circle will not have an inverse function because it's not a function itself. So the first thing, it must be a function. And then, if you look at the new shape, if that also is a function, satisfies the rule, the vertical line test, then we call it an inverse function rather than an inverse relation. So how do we test? Well, if I'm looking at the original graph, using the vertical line test that we talked about tells whether it's a function. Well, if I use a horizontal line test, I can tell whether it has an inverse function. Using the same idea. If at any time that horizontal line cuts it more than once, it won't have an inverse function, but it'll have an inverse relation. So looking at our shapes over there, the parabola, no good, okay? Because it would cut, a horizontal line would cut it twice. Hyperbola is fine, it will only cut it once. Cubic is fine, it'll only cut it once. So visually that's how we could tell. Now using algebra, how we could tell is to say, we'll swap the x and the y's round, but if we then make y the subject of the new one, and it's unique, then it's an inverse function. Now, what do I mean by unique? I mean only one possible answer. So here's y equals x squared. As I say, fails the horizontal line test, so no good. If I use the other idea, I'd say, well, x equals y squared. So y equals plus or minus. Two possibilities. No good. Right? You only have one possibility for it to be an inverse function. So not unique. Whereas that's a very bad drawing of a cubic, but anyway. Horizontal line test, doesn't matter where I put that in, it'll cut it once. If I use the other idea, well, x equals y cubed would become y equals the cube root of x. We don't say plus or minus the cube root of x. There is only one cube root of x. So it is unique. So yes, that has an inverse function. With inverses, a beautiful thing happens. If you sub a function into the inverse function, they should cancel each other out, and you're left with x. And the reverse is true too. If you sub the inverse function into the function, again, they should cancel each other out, and you're left with x. So let's have a look at this function. It is a function. That would turn out to be a hyperbola. It's been shifted a bit, but it's certainly a function. Let's work out its inverse function by swapping the x and the y. So it's x equals y minus 2 and y plus 2. I want to make y the subject. Bit of algebra to be done, but eventually we get there. There's the inverse. Y equals 2x plus 2 on 1 minus x. So I'm going to test it. So first of all, I'm going to sub the original function into the inverse. So everywhere I see an x, I'm replacing it with x minus 2 on x plus 2. So here we go. Well, fractions on fractions, we don't like that. So the first thing I'm going to do is multiply everything by x plus 2 to get rid of those denominators. So I'll get 2x minus 4 plus 2x plus 4 on the bottom, x plus 2 minus x plus 2, 4x and 4. Yes, that is simply x, so it works. And just to prove it, we'll go the other way around as well. Let's substitute the inverse into the original function. So this time, everywhere I see x in the original function, I'm substituting in 2x plus 2 on 1 minus x. Once again, we've got fraction on fraction. I'll multiply everything by 1 minus x this time. And playing around with our algebra once again, yep, we end up with just x. It does cancel and get back to that original thing. Drawing it. This is just some random curve. If I want to draw its inverse, I said it was a reflection in y equals x. So I'll draw in y equals x. Now obviously any point on y equals x would stay there. Let's see it. Whoop, there it is. Okay, so that point stayed the same. If I was going to draw these, I look at key points like these turning points, and I'll get a ruler, hold it at 90 degrees or perpendicular to the y equals x, and then plot it and even them out the other side. And I just do as many points, x-intercept, 90 degrees across to the y-intercept, x-intercept to the y-intercept, and so on. And eventually, you start getting the shape of the inverse. And if you hold your head at 45 degrees, you'll see, oh, look at that. It is symmetric. It does work there. So that's how you can actually draw one. Okay. Well, handful of questions. As I said to you, we won't be tested on that this year. It won't be till, I think we look at inverse functions term 1 in year 12. But, yeah. By looking at a little bit of it today, then when we do look at it next year, it'll be a little bit familiar, and we'll go from there.